Now let us move on to the first question in the exercise. The question is to prove that root 5 is irrational. So let's move on to the solution. So to prove root 5 is irrational, let us assume the contrary. That is, root 5 is rational. Since root 5 is rational, it can be expressed in the form of p by q. Therefore, root 5 can be written as p upon q, where p and q are co-primes. From this expression, we have p is equal to root 5 times q. Now squaring on both sides, we have p square is equal to 5q square. Let this be equation 1. Since 5 divides p square, 5 also divides p. Therefore, 5 is a factor of p. Since 5 is a factor of p, p can be expressed as 5 times of c, where c is some constant. Now we square this equation, that is p square is equal to 25c square. Now we shall substitute the equation p square is equal to 25c square in equation 1. So we have 25c square is equal to 5q square. So 5 goes in 25 5 times. This implies 5c square is equal to q square. From this equation, we have 5 divides q square, which also implies that 5 divides q. Therefore, 5 is a factor of q. Therefore, we have obtained two statements. From those, we can conclude that 5 is a factor of both p and q. This brings a contradiction to our assumption that p and q are co-primes. This is because of our wrong assumption that root 5 is a rational number. Therefore, root 5 is an irrational number. Now let us move on to the second question. The second question is to prove that 3 plus 2 root 5 is irrational. So let's move on to the solution. To prove 3 plus 2 root 5 is irrational, let us assume the contrary. That is, 3 plus 2 root 5 is irrational. Since we have assumed that 3 plus 2 root 5 is irrational, it can be written as p upon q, where p and q are integers and also co-primes. Therefore, this can be written as 2 root 5 is equal to p by q minus 3. On transposing 2 to the right hand side, we have root 5 is equal to 1 by 2 times p upon q minus 3. On taking LCM q on the right hand side, we have 1 by 2 times p minus 3q by q. Since p and q are integers, 1 by 2 times p minus 3q by q is a rational number. Therefore, from the above equation, we obtain root 5 is a rational. But this is a contradiction because we have already proved that root 5 is an irrational number. The obtained contradiction is due to our wrong assumption that 3 plus 2 root 5 is a rational number. Therefore, 3 plus 2 root 5 is also an irrational number. Now let us move on to the third question. The question is to prove that the following are irrationals. So now let's move on to the solution. We shall consider the first bit. So we need to prove that 1 by root 2 is an irrational. For this, let us assume the contrary. That is, 1 by root 2 is a rational. Since we have assumed that 1 by root 2 is a rational number, so 1 by root 2 can be written in the form of p upon q, where p and q are integers and also co-primes. This implies root 2 is equal to q upon p. Since q and p are integers, q upon p is a rational number. So this statement gives that root 2 is also a rational number. But this is a contradiction because we know that root 2 is an irrational number. The obtained contradiction is due to our wrong assumption that 1 by root 2 is a rational number. Therefore, 1 by root 2 is an irrational number. Now let us move on to the solution of the second bit. So in the second bit, we need to prove that 7 root 5 is an irrational number. So to prove 7 root 5 is an irrational number, let us assume the contrary. That is, 7 root 5 is a rational number. Since we have assumed that 7 root 5 is a rational number, 7 root 5 can be written in the form of p upon q, where p and q are integers and co-primes. So this can be written as root 5 is equal to p upon 7q. Since p and q are integers and 7 is also integer, p upon 7q gives a rational number. This implies that root 5 is also a rational number. But the obtained statement is a contradiction. As we already know, root 5 is an irrational number. This contradiction is due to our wrong assumption that 7 times root 5 is a rational number. Therefore, 7 root 5 is an irrational number. Now let us move on to the solution for the third bit. So in the third bit, we need to prove that 6 plus root 2 is an irrational. So to prove 6 plus root 2 is an irrational, let us assume the contrary. That is, 6 plus root 2 is a rational. Since we have assumed that 6 plus root 2 is a rational number, 6 plus root 2 can be written in the form of p upon q, where p and q are integers and also co-primes. This implies on transposing 6 to the right hand side, we have root 2 is equal to p upon q minus 6. This implies root 2 is equal to, taking q as LCM, we have p minus 6q upon q. Since p, q and 6 are integers, p minus 6q upon q in the right hand side is a rational number. This implies that root 2 is also a rational number. So the above equation implies root 2 is a rational number. But this is a contradiction. As we already know, root 2 is an irrational number. The contradiction is obtained due to our wrong assumption that 6 plus root 2 is a rational number. Therefore, 6 plus root 2 is an irrational number. Now we shall prove root 2 is an irrational number. So let's move to the solution. To prove root 2 is an irrational number, let us assume the contrary, that is root 2 is a rational number. Since we have assumed that root 2 is a rational number, root 2 can be written in the form of p upon q, where p and q are integers and also co-primes. This implies p is equal to root 2 times q. Now squaring this on both sides, we have p square is equal to 2q square. Let this be equation 1. This can be written as p square by 2 is equal to q square. From this we understand that 2 divides p square, which also implies that 2 divides p. Therefore, 2 is a factor of p. Since 2 is a factor of p, p can be written as 2 times c, where c is some constant. Therefore, we substitute the value of p in equation 1. So we have 2c whole square is equal to 2q square. This implies 4c square is equal to 2q square. This gives 2c square is equal to q square. So this expression can be written as c square is equal to q square by 2. From this expression, we see that 2 divides q square, which also implies that 2 divides q. Therefore, 2 is also a factor of q. Hence, we have obtained two statements that 2 is a factor of p and 2 is also a factor of q. Therefore, p and q have 2 as a common factor. But this is a contradiction, because we have assumed in the beginning that p and q are two integers and also co-primes. Therefore, the obtained contradiction is due to our wrong assumption that root 2 is a rational number. Therefore, root 2 is an irrational number. Now we shall prove that root 3 is an irrational number. So let's move to the solution. To prove root 3 is an irrational number, let us assume the contrary, that is root 3 is a rational number. Since we have assumed that root 3 is a rational number, root 3 can be written in the form of p upon q, where p and q are integers and also co-primes. So this can be written as p is equal to root 3 times q. Now we shall square this on both sides. This gives p square is equal to 3q square. Let this be equation 1. So this can be written as p square by 3 is equal to q square. So from this expression we see that 3 divides p square, which also implies that 3 divides p. Therefore 3 is a factor of p. Since 3 is a factor of p, p can be written as 3c, where c is some constant. So now we substitute the value of p in the equation 1. This gives 3c whole square is equal to 3q square. It is 9c square is equal to 3q square, which implies 3c square is equal to q square. This implies c square is equal to q square by 3. From this expression we see that 3 divides q square, which also implies that 3 divides q. Therefore 3 is also a factor of q. So we have obtained two statements, that 3 is a factor of p and 3 is also a factor of q. Therefore 3 is a common factor for both p and q. But this is a contradiction, because we have assumed in the beginning that p and q are two integers and also co-primes. The obtained contradiction is due to our wrong assumption that root 3 is a rational number. Therefore root 3 is an irrational number.